Welcome back to lecture. This is section 5.2. We're going to kind of continue talking about random variables. We did that in 5.1. But in this case, there are certain random variable distributions that are well understood. This one, the first one that we're going to study is called the binomial distribution. So let's take a look at this and see if we can figure out how to work this. So our objectives, we're going to determine whether a random variable is binomial. We have to look and see if we can find these characteristics to define it as a binomial random variable. And if it is, we're going to be able to write the probability distribution and then compute binomial probabilities. And then at the very end, we're going to do the mean and variance of a binomial random variable, just like we did just a simple random. But in this case, it simplifies even further. So consider this example. Suppose that your favorite fast food chain is giving away a coupon with every purchase of a meal. 20% of the coupons entitle you to a free hamburger, and the rest of them say better luck next time. 10 of you order lunch at this restaurant. Okay. Here's what we would like to know. We want to know the probability that 3 of you win a free hamburger. Okay. So we go, 10 of you go into this restaurant. We get these coupons. 20% of them entitle you to a free hamburger and the rest of them don't. And basically we're going to start asking these questions. Well, out of the 10, what's the probability that none win a hamburger? What's the probability that exactly 1, 2, 3 will continue down to all 10 of them? And then we can ask the other type questions. Well, what's the probability that 3 or less received a free hamburger? Okay, so that kind of combination of things is called a binomial distribution. And a binomial distribution, the one that, if we just look at the one that we just described, each time we examine a coupon, we call it a trial. So there are 10 trials. They're basically 10 samples that we're pulling in, and then we're asking the question, how many out of that 10 are successes, 0 through all 10, okay? Each time we get a coupon, for this case is a free hamburger, we call it a success. The random variable X represents the number of successes in 10 trials, 0, 1 through 10. So that would be that would have 11 random variables that we're concerned with, and then the probability of each one for our distribution. So a random variable that represents the number of successes in a series of trials has a probability distribution called the binomial distribution. The conditions are, so as we're reading a problem and we're seeing if we can use the binomial distributions, we're looking for 1, a fixed number of trials are conducted. So a sample of 10 people is basically what we're doing. There are 2 possible outcomes for each trial. One is labeled success and the other is labeled failure. We don't consider multiple ones. It's either success or not success. The probability of success has to be the same on each trial. Let me move you back up. The trials are independent. This means that the outcome of one trial does not affect the outcomes of the other trials. Remember, we've looked at replacement and not replacement. We have to have a situation of replacement or large enough that when we pull these, that one trial does not affect the other trials. So the random variable X represents the number of successes that occurs. So N is the number of trials. P is the probability of success that we're going to look at. So here a fair coin is tossed 10 times. Let X be the number of times the coin lands head. Is this a binomial experiment? So basically it is. Each toss of the coin is a trial. There are 2 possible outcomes, heads and tails. And then X represents the number of heads. Heads counts as a success. So the trials are independent because the outcome of one coin toss does not affect the other tosses. Okay, so basically we're going to have, say, 0 where none were heads all the way up to X number of times that we do the experiment. Now consider this one. Have 5 basketball players each attempt a free throw. Let X be the number of free throws made. Is this a binomial experiment? Okay. So in this case, it's not. The reason being is the probability of success making a shot differs from player to player. So it would all depend on each individual player that we would have to do, because they would not all be equally skilled at making free throws. 10 cards are in a box. 5 are red, 5 are green. 3 of the cards are drawn at random. Let X be the number of red cards drawn. Is this a binomial experiment? So note that this is there are only 10 cards in a box. Each one of these cards that we pull changes the probabilities that the rest of them would be red, and it all depends on if we pulled an initial red or initial green. So that's not an independent experiment. They're dependent. This is not a binomial experiment because the trials are not independent. So let's look at a probability distribution. How would this look out? So what if we did this experiment, we grab out of a certain number of trials, can we calculate the probabilities from the 0 up to the X? Okay. So consider this one. Excuse me. Consider the binomial experiment of tossing 3 times a biased coin that has probability 0.6 of coming up heads. So in this case, it's not a fair coin, not a 50-50 coin. So let X be the number of heads that come up. If we want to compute the probability that exactly 2 heads, that exactly 2 of the tosses are heads, there are 3 arrangements of 2 heads and 3 tosses. 3 tosses, and I'm looking at exactly 2 successes. So what would this look like? If I get exactly 2 successes, I would have 2 heads. I could do 2 heads and a tail, or a head, tail, head, or a tail, head, head. Each one of these are 2, and that's the only way that I could get 2 heads out of the 3 tosses. Okay. So what's the probability of the heads, heads, tails? Well, that's the probability of the heads times the probability of the head times the probability of the tails. Each one as we go through. Okay. So that would be 0.6 squared times 0.4. Similarly, the HTH, this is the very same thing, 0.6 squared times 0.4, and as well as the TH8 is 0.6 times 0.6, 0.4, 0.6, 0.6 is all that very same number once we multiply them out. So each one of these are the very same thing. I've just got 3 of these, so it's either this or this or this. So my probability is just 3 times that by the addition rule. Okay. So in examining this result, we see that the number 3 represents the number of arrangements of 2 successes and 1 failure. In general, this number will be the number of arrangements of X successes and N trials. So we have the N trials and then the 2 successes out of that. Okay. This is how many ways that we can do this. And this is what we looked at previously at the end of chapter 4 about this calculation being n factorial divided by x factorial n minus x factorial. That's that notation where the order doesn't matter, but I just want to know how many ways that I can count that up. So in general, for a binomial random variable x, the probability of exactly x is how many different ways we can count these things up. So this is the probability of x successes. So P, these are all the successes, and then the rest of them are failures or 1 minus P. And then since there are several ways, this actually gives us the number of ways that this can, that this arrangement happens out of the x trials. So let's see if we can do a couple of calculations, different methods. So the Pew Research Center reported in a recent year that approximately 30% of U.S. adults own a tablet computer such as an iPad, Samsung Galaxy Tab, or Kindle Fire. Suppose a simple random sample of 15 people is taken. Use the binomial probability distribution to find the following probabilities. Find the probability that exactly 4 of the sample people own a tablet computer, that fewer than 3 own a tablet computer, that more than 1 person, and the number of people between 1 and 4 inclusive. So the first one is to find the probability that exactly 4. N is 15, so let's see. Here's the 15, choose 4. This is the notation for out of the 15 trials, exactly 4. So this calculation, you can find this in your calculator under the probabilities. Different calculators doing different things. We'll probably work on this during labs. But it's basically the 15 factorial, the n factorial. Here's the x factorial. And then 15 minus 4 factorial. And then this would sound, simplify out. 0.3 is the probability of success. Exactly 4 of those are successes. The rest, 15 minus 4, which is 11, is the failures. Those are the n, the 1 minus the p, which is the 0.7. So the probability of 0.4 would be the 0.219. Fewer than 3, we would need to do fewer than 3 is 0 or 1 or 2. We would have to do this calculation 3 times. Here is the probability of 0. 15 choose 0 is how this is read. 0.3 to the 0, the success is no successes. 1 minus 0.3, the probability of failures, and the 15 minus the 0 successes, all 15 are failures. Here's the 1 success, 14 failures, 2 successes, 13 failures. And we add this up because it could be the 0 or the 1 or 2 that we're interested in, or the events that we're interested in. So we add these numbers up and it gives us a probability of 0.127. More than 1 person owns a tablet computer. More than 1 is 2, 3, 4, 5. So we could use the rule of complements. We could find the more than 1 is 1 or fewer. We could calculate the 0 or 1, just like we did last time, but we don't include the 2. And then the complements is 1 minus the p, 0 or 1, which is the more than 1. So that is 0.965. The number between 1 and 4 inclusive. Well, I could just add these up, 1, 2, 3, or 4. 15 choose 1, 1 success, 14 failures, 2 successes, 13 failures, 3 successes, 12 failures, 4 successes, and 11 failures. And we just add up, once we do the calculations, we just do that, add them up as the 0.511. So there's also tables in the back of the book that we can go to and help us calculate these things. It only works for certain ones. You'd have to go to a bigger table of probabilities, a binomial probability book to get everything that you would want. So here, I'll kind of show you what I mean. The Pew Research Center reported in a recent year that approximately 30% of U.S. adults own a tablet computer such as an iPad, Samsung Galaxy Tab, or Kindle Fire. Suppose a simple random sample of 15 people is taken. Use the binomial probability distribution to find the following probabilities. And these are the ones that we just did. Doing it by hand, we're now going to go look at some tables. Okay, so this is the binomial tables. If we go to the tables at the end of the book, they're in the appendix. I think it's the A. And it basically is laid out like this. And let me kind of tell you, I've got a P up here. This is the probability of successes, and it only works for like 0.05, 0.10, 20, 25, 30. So these are only in increments of 500ths. Luckily, this is the P.3. That's the probability that's in there. But not only do we have probabilities, we also have to go through the tables and find out a corresponding value of trials. So there will be like n is equal to 2, 3, 4, all the way through 15, 16, 17. You have to locate that one, locate your probability, and then say exactly what am I looking for. Find the probability that exactly 4. So here's my probability of exactly 4. If I assume the probability of success is 0.30, that probability using that intersection of 4 and here, the probability of exactly 4 with a 30% probability is 0.219, okay? What about fewer than 3, which is the 0, 1, or 2? Then I would just add up. I'd do the very same thing. I'd go to my table. Here's my 15 trials. I'd go through a list of tables, find the one that has 15 trials. I'd go across my probabilities. Do I have a matching one? Yeah, there's 0.30. Probability of 0, 1, and 2, those three, 0, 1, and 2, and I would just add them up because I'm looking at fewer than 3, which is the 0, the 1, or the 2. So more than one person is the, now this kind of shortened up the table because they were only focused on here, but again, this is going to go 0 through 15. And more than one is all of these. I could go and add up to, let me go backwards. I could go up and do the 2 all the way through. Well, they didn't include this all the way to 15 either. But you would go all the way through and add those up. But in this case, it's easier for me to just add these up, the 0 or the 1, and then go 1 minus that. So this is 0.036. There's the probability of 0, 1, and the rest, more than 1, is just 1 minus that, and that's the rules of complements. Between 1 and 4, I just go through and I go across the table. Here's my 30, number of trials 15, and this would go all the way down to 15, but all I'm concerned with is 1, 2, 3, or 4. Inclusive means I include 1 and the 4. If I said between 1 and 4 exclusive, that meant exclusive of 1 and 4, and I would just add up the inside the 2 and the 3. But that would give me, when I add up all these, the 0.511. There's the 0.031, the 0.092, the 0.172, and then the 0.219. The TI-84, the TI-36 as well, offers you the ability to calculate probabilities with the calculator. Okay, this is a binomial distribution. There are actually several distributions in here. Here's these things. If I go in, let's kind of put me down here. The TI-84 calculator, there's 2 primary for computing binomial probabilities. There's other ones. There's the t-distribution we'll see later on. There's the normal distribution of Poisson, a chi-squared. Here's the f's. But this is the 2 that I'm concerned about with binomials, is binom. There's 2 versions of this, PDF and CDF. The PDF is the one that says exactly this. So you would, if you were going to do what's the probability of exactly 2, then I would use the PDF with the 2. The CDF would be all the way up including that. So if I said binom CDF with the 2, I would be saying give me the probability of a 0 or a 1 or a 2. So here when I'm doing the x, it is less than or equal to a specified variable, and then this x is equal to a specific one. So we'll see how to put this in. So when I'm doing binom PDF, the later 80, the 84s, will actually give you this in a wizard where it says, give me the n, give me the p, give me the x. But for the earlier versions and the 83, I think you're going to have to type this in on the command line, do your parentheses, and you're going to have to enter how many trials you're talking about, say 15, probability 0.303, 0.3, and then x is the exact number. So exactly x. And the CDF, when I did the x, it would add up the 0, the 1, the 2, all the way up to the x. So we're going to do the very same thing and do it, enter them what we would do on a TI-84. So exactly 4, I would say out of the 15 trials, binom PDF, exactly 15 trials, a probability 0.3, exactly 4 exactly 4 would be the 0.218623, and we would round them off to, let's say, maybe 4 decimal numbers, 0.2186. If I did to 3, I would bump that. Since this is bigger than 5, I would go to 0.219, okay, to 3. Fewer than 3. Fewer than 3 is a 0, 1, 2. I don't include the 3. So I do the CDF in this case with the 2, and that would add up the probabilities of the 0 plus the 1 plus the 2, and would give me the 0.1268. More than 1, again, I would do the binomial CDF. Since it's more than 1, I do the 0 and the 1. I can do the CDF, which would give me the 0 or the 1 calculation, and then 1 minus that would be the more than 1 person. 1 and 4 inclusive. I would do the binomial CDF. Since I'm doing the 4, I'm doing all the way, I'm summing up all the 4, and then I want the 1, so I'm backing off and subtracting off the 0. So this is 4, 3, 2, 1, subtract the 0 because this is 4, 3, 2, 1, 0, and I'm subtracting that off. So I'll back off 1 between the 1. Okay. So it turns out it's actually pretty easy, given the probability, the number of trials to calculate the mean and the expected value, the expected value of this, and the variance or the standard deviation. The mean is simply, I've got a number with a probability of success. So this is the percentage of those that we are expecting to be successes, okay? So the mean is just n times p, the mean number of successes. The variance is, this is the square, so it's the standard deviation square, is n times p, 1 minus p. This 1 minus p is also usually shown as q. Q is equal to 1 minus p, so npq, the not successes. So this is the probability of success times the probability of not success. And then we need to take the square root of that to get the standard deviation. So the square root of np, q, or 1 minus p. So the probability that a new car of a certain model will require repairs during the warranty period is 0.15. A particular dealership sells 25 such cars. Let X be the number that will require repairs during the warranty period. Find the mean and standard deviation of X. So if I do the 0.15 times the 25, here's the mean. 25 trials, probability of success. The mean number that I would expect it to require repair is the 25 times 0.15, 3.75 on average. The standard deviation, 25. 0.15, I'm taking the square root after I do this, the 1 minus the 0.15 or 0.85. So once I do that, that should be 1.785. Okay. So these are the things that we talked about: how to determine whether a random variable is binomial, constant probability across all the trials, a set number of trials, and then we go through and count those. The notation for a binomial experiment, how to determine the probability distribution of a binomial random variable, how to compute binomial probabilities, and then how to compute the mean and variance of a binomial random variable. So go back and review. I hope you found this useful, and we'll see you next time.